Okay, in this one, I've got a crate being pulled up on a pulley system using a motor as shown. Okay, I has a speed of 4 meters per second after traveling 8 meters along the plane, and wants to know the power that must be supplied after it's moved this 8 meter. Once I get up to 4 meters per second, what is the power that I need to apply to that motor? So again, I've got an efficiency given there. So again, the efficiency equation is P out over Pn, where Pn is really what I'm trying to calculate here, right? That's the power that the motor has, okay? My output, okay, is defined as force times velocity, right? So if I can find the force on that cable as it's pulling it up, okay, I know the velocity is 4 meters per second. That's given in the problem statement. So if I can find the force on that, that will help me figure out what the power is, and so on and so forth. So the first thing I need to go through is try to figure out what that force is. Okay, and again, I've got velocities at different positions, right? Velocity 8 meters. I've got 4 meters per second after 8 meters, right? So I'm going to use that to help me calculate what the force in the the string is in that cable, right? So I'll use KE1 plus that equals KE2. That's the work being done from 1 to 2, okay? And again, this thing starts from rest, I believe. Yep, starts from rest. So my initial kinetic energy is 0. Again, I know my final kinetic energy, that's from the 4 meters per second. We'll get to that in a second. We just need to talk about the work being done. Okay, so before I get too far into what the work's being done, let's talk about the forces that I've got on this thing. So I've got 50 times 9.8, and that's the weight acting straight down. Notice I've got actually two forces here, so I'm going to call this 2F, okay, right there. That's the force in that cable, right? I've got a normal force. It's not going to do any, because it's perpendicular to motion, it's not going to do any work, so I don't really care what that is. I only need it because I know that as this moves up, friction is going to oppose it downward, and that's going to be 0.3 N, right? So let me sum my forces in this direction here, where this is going to be at 30 degrees, and from that I can find that my N is going to be equal to 50 times 9.8 times the cosine of 30. Okay, and again, this is really only to help me find what my friction is. Okay, because the normal force is not doing any work at all. Okay, but it's 424. So I've got that. And that's going to help me find my friction. Okay, so again, what's doing work? Well, that rope is doing work. 2F is doing work, and it's doing it over 8 meters. Okay, in the direction of motion, positive work. Okay. Friction, negative work, because it opposes motion. 0.3 times what I just found, 424, and it does that also over 8 meters. Okay. Then I've got gravity doing a little bit of work. Okay. Gravity's down, motion is up, it's going to be negative. Now, the only part of the gravity that I care about is the part along the incline, which is going to be sine of 30 of that. So it's going to be 490 times the sine of 30. And again, the 490 is just 50 times 9.8. Okay. And it does this over 8 meters. Okay. And again, the normal force does absolutely no work at all. Okay. So from this, I find 16F, okay, minus 2978. Okay. So the motor's doing a lot of work, or that cable's doing a lot of work, friction's doing negative work, and then a component of the gravity is also doing negative work because friction and gravity are going downward. This thing's moving upward, so it's negative. Okay. Um, and my final kinetic energy then is really known. It's going to be 1/2 times the mass of that thing, which is 50, times velocity, which is 4 squared, and that equals 400. Okay, so now I can very simply say 16 times F minus 2978, right, equals 400. And from that, I can find the force in that cable equals 211 newtons. Okay, now knowing that, I can come back up here and determine, okay, well, what is the power output? Well, again, I still got two of these forces on there, so I probably didn't, anyway. Right, so the force, my output is that box moving, and the force on that box is two of these forces that I just found, right? So it's 2 times 211, and its velocity again is 4 meters per second as given in the problem statement, okay? Which gives me the output power of this box moving of 1689, and that's Newton meters per second, okay? Now I can come up here, which that is watts, by the way. A Newton meter per second is a watt, okay? Um, I want to find my input power, okay? And that's going to be my output power, 1689, divided by my efficiency of 0.74. And from that, I get my input power of 2283 watts. Okay. So again, whole thing is I've got to find my output power. That's most of the problem here, where I find my force times velocity. Okay. And I can find that force using the work energy principles that we've talked about, where I've got my kinetic energy, the work equals the final kinetic energy to find that force. Once I have that force, I take it times its velocity to figure out the power output, and then divide that by the efficiency to get the input needed to the motor.